Hey, sorry to have you watch two screencasts in one night, but sometimes this is just going to happen. Force versus distance graphs. It's a quick screencast, but it's very worthwhile. So here's the deal. We often use force versus distance graphs to analyze the energy of a situation because force times distance equals work. So with that in mind, it should be pretty obvious that if I have 200 newtons worth of force acting across a distance of 8 meters, I'm going to do some work. In fact, I'm going to do 1600 joules worth of work. Now, so we're going to start off with just a constant force. You see 200 newtons. If I take the area under here, 200 times 8 meters, I get 1600 joules. So let's just say I have an object that initially had 400 joules worth of kinetic energy. I did 1600 joules worth of work on it. It's now going to have 2000 joules worth of kinetic energy. All right. Now, what if I have a negative force? So just keep in mind, when we describe situations, we're almost always going to say set the direction of initial motion as positive. Therefore, a force acting in the other direction is a negative force, and it's going to do negative work. It's going to reduce the kinetic energy of the object. So in that case, I'm going to say negative 150 times 4. So negative 150 times 4 is negative 600 joules worth of work. So if the object again had 1,000 joules to start with, it's now going to have 1,000 joules minus the 600 that I did, and that means it's left with 400 joules worth of kinetic energy. But what about this? What if the object didn't have 1,000 to start with? What if instead the object initially had 400 joules? So if it was traveling to the right and it had 400 joules, and I did 600 joules worth of negative work. Well, really what happens is this. The object is going to slow down and stop after I've done 400 joules worth of work, and then I'm going to do another 200 joules worth of positive work. But if I just do it this way, it's really easy to say, well, I end up with negative 200 joules, but since there's no such thing as negative energy, I just have 200 joules of kinetic energy, but I'm going the other way. Now, this should be something we're pretty comfortable with at this point here. If the force is going down at a constant rate, as it is here, I have this slope here. Well, then if I want to find this area, it's just going to be the maximum force uh, times the distance divided by 2. All right. So in that case, I have 300 times 8 divided by 2. That gives me 1,200 joules. So if the object was initially traveling with, if it had 400 joules worth of kinetic energy, now it's got 400 plus 1,200, it's got 1,800 joules of kinetic energy. And if I know the mass of the object, I can figure out its velocity. All right, let's just take one this kind of puts it all together here, and then we'll be done. All right, so I've got this graph. It shows force acting on a 20 kilogram, I know the mass, object that's initially traveling at 10 meters per second. All right, and here's what I say. I have 100 newtons of force is going to act across a distance of 10 meters. Then that force is going to gradually decline until it reaches 0 at 20 meters. So I want to figure out what's the final velocity of the object. So here's how we're going to approach this. Forgive me if I just draw this out a little bit. So the first thing we're going to do is we're going to figure out what's the total work done by looking at the area under the curve. So I have 100 times 10. So there I have it. That's going to be 1,000 joules worth of work there. Now I have 100 times 10 divided by 2. So that's another 500 joules here. So a total area under that line is 1,500 joules of positive work done on the object. So it's gaining kinetic energy, it's gaining 1,500 joules of kinetic energy. Now, work is equal to the change in energy. So I could say, well, work therefore equals the kinetic energy that I end up with minus the kinetic energy I started with. Therefore, the kinetic energy I start with plus the work I did tells me the final kinetic energy. All right. So kinetic energy, recall, is equal to 1/2 mv squared. And I happen to know the m and the v here, so I can see what my starting kinetic energy is. And in this case, 100 squared times half of 20 gives me 1,000 joules worth of kinetic energy that the object started with. And then I did an extra 1,500 joules worth of work to it. So now it ends up with 2,500 joules worth of kinetic energy. So I want to know how fast is it going? Well, it has a mass I know, and I know the kinetic energy. So I can simply solve this equation using substituting this for its kinetic energy and solve it for V. And when I do, I get 15.8 meters per second. So it was going 10, and now it's going 15.8. Not so bad. Thanks for watching.